Hi everyone, this is Weiwei Guo. I'm going to talk about the query and user understanding session. In this session, I will introduce several representative algorithms for the query and user's understanding. So at the core of all the algorithms is the sequential modeling. This is to use CNN or LSTM or transformer to model the sequence data. The sequence data could be a sequence of text tokens, or it can be a user behavior sequence. By adding different loss functions on the deep learning models, we have the representative algorithms. For example, if we can add the softmax loss to predict the sequence label, which is the classification task, and one application is the user intent. We can also predict a label for each of the word, and this is called sequence labeling. One example is the name entity recognition on the query and the documents. Also, from one query, we can predict the most relevant document, and this is well known, the ranking task. And from a partial sequence, we can generate a complete sequence. This is the sequence completion task. An application is a query auto-completion. Note that this is already a language generation task. Another language generation task is the sequence generation from one sequence to the next sequence. An application in the search system is a query suggestion. At last, we have the representation learning task, BERT pre-training. The BERT pre-training uses a lot of unsupervised language data, and it is supposed to improve the accuracy of all the 5 representative algorithms. In the rest of the talk, I will focus on introducing each of the 5 representative algorithms with a real-world example in the search and recommender system. Okay, let's get started with the classification task. In this task, I will use the user intent as an example in the search and recommender system. The user intent is the first step of a search and recommender system. It tries to identify what kind of information the user is looking for in this system. For example, at LinkedIn, people may use LinkedIn to search for their friends, or to look for jobs, or to looking for some courses in the learning search. Another example is the IMDb, where a lot of information about the movies are available. People use IMDb to look for cast or showtime and location of a movie or the plot of a movie. At last, the example is ESPN, where people check the latest sports news, such as scores or the match schedules or the information in the specific team. There are many applications of the user intent. The first direct application is to identify the search verticals given a query. So in this example, the query is research scientist remote, and therefore it is very likely that the user intent is to look for jobs instead of looking for people or content or company or schools. And also the user intent can be used as a feature in the search result ranking or blending. So here, the intent is use a feature to blend the people search result as well as the job search result to maximize the click-through rate. Also, it can be used to trigger question answering component. So in Google, if you type in Green Book cast, and then it identifies that this is some information that is directly stored in the database, and then they can directly returns the actor in this movie. So usually the user intent is treated as a text classification problem. The traditional method will use a lot of sparse features, such as the back of words features, the n-gram features. The models are usually shallow models, such as logistic regression, naive Bayes, or SVM. For deep learning method, the first step is to convert the word into word embeddings and then apply models such as FastTest, CNN, LSTM, and Transformer. Now let's look at the details of the deep learning approaches. So the input is a word sequence that is the query and the handcrafted features. The handcrafted features could be a lot of the user behavior features. For example, how many times the user search for people result at LinkedIn and how many times the user search for job result at LinkedIn. And then the next step is to convert the word sequence into a fixed length text embedding by applying CNN or LSTM or BERT. And then you can combine the text embedding features and handcrafted features through a fully connected layer. So the hidden layer contains a lot of nonlinear feature about the text embedding and the handcrafted features. And finally, based on the hidden layer, you can predict the intent. So this is a practical model in the industry because it made use of the powerful handcrafted features combining with the deep learning models to get the best relevance performance. The next representative task is sequence labeling. Here we use name entity recognition to illustrate the idea, which is widely used in the industry. So the goal of the sequence labeling is to identify the key concept in the sequence of words. In the document side, we want to identify the Washington DC is a location and George Washington is a person. We can also apply on the query side. We want to identify Pinterest is a company and program manager is a job title. It has a lot of application in the whole search and recommendation pipeline. In the retrieval phase, we want to ignore the unimportant words in the query. Given a query looking for a research scientist job, we would like to only use the research scientist to do the retrieval. And then we can also construct a lot of powerful features in the ranking phase. Firstly, we want to extract the key concept from the document so that the document with the key concept should be, with the key concept matching should be ranked higher than the document without the key concept matching. It can also be used to resolve ambiguity in the user intent. If the user is looking for a job posted by the S&P company, then we should not return any jobs that list S&P as a skill. Now let's look at how people address this problem. The naive approach is to perform classification on each word. So given a query, Pinterest program manager, the first step is to do feature extraction. And then you can extract a lot of features from the whole query for the word Pinterest. And then perform logistic regression to predict the tag. The same model is applied to the other words, such as program and manager. Let's look at what the features are. There are two kinds of features. The first kind of features are the sparse features similar to the text classification problem. For example, whether the current word is manager, whether the current word is research. The second kind of features are from a lexicon, which is constructed from our domain knowledge. The lexicon will tell us whether the word has a title match or whether the current word has a company match. One obvious disadvantage is that the word label relations are ignored. Let's look at the word Pinterest. If we have very high confidence that it's a company, then no matter what the next word is, it's very unlikely to be a company. This is because in the LinkedIn queries, there are very few occasions where one query contains two companies. Motivated by this, the researchers proposed the conditional random field to incorporate the relation between tags. In the upper layer, there is no longer logistic regression, but instead it's a CRF layer. As you can see here, the two adjacent prediction is attached by a line. And this means that in CRF, it explicitly modeled the probability of the next prediction. Currently in the industry, the CRF is much more popular than the logistic regression because it provides much better relevance performance. The next slide is how deep learning approach is applied into the sequence labeling problem. The key difference has been highlighted in red. Instead of using the handcrafted features, we use LSTM to generate a dense vector feature. And then the dense vector is able to summarize all the context information into the hidden state. And based on the hidden state of LSTM for each word, the CRF layer is able to better predict the sequence. We have went through two language understanding tasks, classification and sequence labeling. The third task is ranking. I would like to formally define the ranking task. Given a user, a query, and a document, we would like to compute the relevance score to reflect the relatedness. For recommender system, the query is missing. It's just the relevance score between the user and the document. Also, let's begin with the traditional method for ranking. For ranking, the algorithm is basically learning to rank, which will be explained later. The features are also handcrafted features, such as the matching features between the user and the document, and also the matching feature between the query and the document. The third type of features are the document unknown, which is mainly the popularity of the document. In this talk, I will mainly I will mainly introduce two deep learning methods. In this talk, I will introduce two major deep. In this talk, I will introduce two deep learning methods. The first one is called representation-based method. Here, I'm introducing the work we have done at LinkedIn, which has been deployed into our search systems. Now, so the input is the query and the document, as well as the traditional features. By applying the text embedding layer, which is CNN, LSTM, or BERT, we can convert each individual text data into embedding. And then we go through the interaction layer, for example, to compute the cosine similarity between the query embedding and the document embedding to generate the deep features. And then we combine the deep features with the traditional features, go through some hidden layer, and finally we compute the document score. And in training of the ranking, there is a learning to rank layer. Here, I'm showing you a list-wise learning to rank layer, which incorporate the score of the other documents. And then we want to maximize the probability of the click the document. The next method is called interaction-based method. So as you can see here, we can firstly concatenate the query and the document into a sequence. And then the sequence is used as an input for the BERT model. And during each layer of the BERT model, each word in the query and it will be compared with each word in the document. So that's why it is called interaction-based method. And then we also go through the multi-layer perceptron layer and get a final score of the document. I would like to highlight a key difference between this method. That is where the interaction between the query and the document happens. So in this method, it happens on the word level, that is the query word will be compared with each of the document word. However, in the first method, the interaction happens much later on. We have to generate the text embedding for each query or the document field first, individually, and then we can do the cosine similarity or Hardeman product between the embedding, text embeddings. So because of this key difference, the second method has better relevance score. However, it also gives the first method an advantage, which is we can pre-compute the document embeddings. And this is very important to reduce the online computation latency. Because of this key difference, the second method, interaction-based method, has better relevance performance. However, it also gives an advantage for the representation-based method. Because of this key difference, the second method has better relevance performance. During the word level interaction, the embedding can remember how much matching in terms of words between the query and document. It also gives an advantage for the first method, that is the document embedding pre-computing. Document embedding pre-computing is very important to reduce the online serving latency. And because of that, in the industry, the representation-based method is much more popular in the online system. The next task is sequence completion, which is a language generation task. Sequence completion can be applied on both queries or documents. On queries, it is the query auto-completion task. And on documents such as emails, it becomes the Smart Compose task. Throughout this talk, we will focus on the query auto-completion task. There are mainly two goals for the query auto-completion. The first one is it can provide better user experience in the search system. It can speed up the human computer interaction by saving the keystrokes. And in the following example, 80% of the keystrokes are saved. The other goal is to guide users to better search result. This is an example of the prefix SOF. There are two candidates. One is the software developer and the other one is the software engineer. We believe software engineer is a better candidate because this is a more commonly used job title, and therefore it can retrieve more profiles. The query auto-completion can guide the user to better search result by ranking the software engineer higher than the software developers. To build a query auto-completion model, there are mainly two challenges. The first one is limited context. There are only, usually there are only several letters in the query prefix. The other one is latency. For each keystroke the user typed, the query auto-completion result needs to be returned in 50 milliseconds. Now let's look at the traditional method. The traditional method is a two-step approach. It contains a candidate generation component and the candidate ranking component. In the generation component, it will retrieve all the queries that start with a prefix. And then in the candidate generation phase, it will use a lot of frequency features to do the ranking. The drawback of the traditional methods is that it mainly rely on the query frequency, which requires a lot of memory usage. And also it does not use any of the semantic information in the prefix. Let's look at how deep learning approach handle this problem. I will illustrate the idea by using the example of generating the query Java from the prefix JA. Firstly, it will summarize the context, the prefix by LSTM. The input for the LSTM is the two characters, J and A. By the way, this is a character level model. And then it will generate the whole query by bin search. It will perform classification over the vocabulary of characters based on the hidden state. Now it will generate the next character V and send back the next character V to the LSTM and generate the next character A. When a special token is generated, no more character will be generated and the whole process is stopped. In general, the deep learning approach can get much better relevance performance, however, at the cost of computation time. The last task is sequence generation from one sequence to another sequence. It has applications on both query side and the document side. On the query side, here we are going to show an example, which is query suggestion task. The last task is sequence generation from one sequence to another sequence. The sequence generation has applications on both query side and the document side. On the query side, today we are going to show an example, which is query suggestion. Given one query machine translation, we want to suggest the related queries, such as data scientist, artificial intelligence, deep learning, so that the user can click on the related search and issue a new query. The application on the document side is machine translation. This is an example of translating the Chinese feed into the English feed. In terms of traditional method, this query suggestion is usually built on query concurrence information. The query concurrence information extracted from the search log. For example, given when people search the LinkedIn query, for 50 times, the next query will be LinkedIn recruiting. And then collaborative filtering is built on the concurrence matrix. So one obvious issue with this kind of approach is that it treats each query as a unique entity. Therefore, it does not use any of the word semantics inside the query. And also it cannot handle new queries. Motivated by this, the researchers have applied the sequence-to-sequence framework for query suggestion. This is the diagram of the sequence-to-sequence framework. It has mainly two components. One is the encoder, one is the decoder. In the encoder, it is basically an LSTM model that summarizes all the information in the first query. In the decoder, it's an LSTM plus the classification over all the vocabulary. In fact, this is the model that is used for query autocompletion. So the input of the decoder is the last hidden state in the encoder, and then it will generate one word by another until the end of sentence is generated. It is worth noting that this is a very flexible framework where a lot of additional information can be incorporated. In this talk, we will only mention two work. The first work is what we have done at LinkedIn to incorporate the personalized feature into the framework. We have experimented with several models and we find this model produced the best result. The idea is to incorporate the personalized feature as an additional token into the encoder. The benefit of this is that during the decoding, the attention model can dynamically select the useful information in the decoder. Either it's the personalized feature or the original token in the first query to generate the tokens in the second query. The other work is how to incorporate the session information into the sequence-to-sequence framework. The session data is actually the previous query that the user have typed. For example, all the queries that the user have typed in the last week. So now the framework becomes a hierarchical sequence-to-sequence framework. The first layer of the model is a LSTM to summarize the previous queries, and then the output is sent to the second layer of the LSTM. And in the second layer of the LSTM, it will generate the it has the decoder model and to generate the new queries. So that's all the technical details for the representative algorithms for query and user understanding. At LinkedIn, and in fact, we have designed effective deep learning models for all the representative tasks. And the resulting models has been deployed into the LinkedIn's commercial search and recommended systems. In addition, we also open source the code, which is the DTEX package. So DTEX refers to the Deep Text Understanding Framework. Currently, the code contains applications for the three tasks: the user intent, document ranking, and the autocomplete. In the future, we will incorporate the sequence labeling and sequence generation, as well as the representation learning into the DTEX code. More information can be found in this page, including the GitHub link, the link to the LinkedIn's engineering blog. And also we have 5 papers related to the algorithms I just mentioned in the last section. That's all for this session. Let me know if you have any questions. Thank you.